Today I want to talk about reaction rates in a little more detail. And if we're thinking about the rate of an overall process, so we're thinking a chemical reaction here, the overall reaction can be measured by some sort of change in concentration over the change in time. So as the reaction progresses from reactants to products, how much am I losing of my reactants, or how much am I gaining of my products? And so if I'm thinking about my products and reactants as kind of concentrations and how that concentration changes over time, that gives me an indication of how quickly a process is occurring. So that's kind of what we're talking about when we're talking about a reaction rate overall. But how do we tell then which reactant or product we're going to base the rate on? Well, it kind of depends on what we're focusing on, and there's a lot of different factors that go into that. So if we think about a chemical process here, we have reactants. So I have two of my nitrogen dioxides here reacting with one of my fluorine molecules to give me two of my nitrogen dioxygen fluorides, monofluoride. So if I look at this from a molar quantity standpoint, the reason that we balance these coefficients out front in our balanced chemical equation is to give us these molar ratios between the two. So it's not just that there's two of these guys smashing into one of these and forming two of those, although that is what's occurring. We could say that there's 2 moles of these molecules reacting with 1 mole of these, giving me 2 moles of my product. So if we think about this as having some sort of rate, so this process has a rate, and if we kind of think about that like an energy, because there's energy that's sort of built into how quickly something occurs, then I have sort of a 1-to-1 ratio with my 1 molar thing here and the rate. So I could think about this as a change in my concentration of fluorine over a change in time. So I have my deltas there that indicate a change. These brackets here indicate concentration. Now concentration has a number of different units to it, but we usually think about concentration's SI unit as molarity. So this could be a change in molarity over a change in time. And usually for time, our SI unit for that are seconds. Okay, so if I'm looking at the change and how this thing changes over time, by convention, we would say, well, if this process has an overall rate, and this overall rate is always positive, right? Because if we're thinking about how quickly something is occurring, I can't have a negative quickness to it, right? It would be like having a negative velocity in a car. That just doesn't happen, right? So the rate itself has to always be positive, but relative to that rate, by convention, we say that the reactants here are going down, right? We're losing them, and so we're going to call this a negative relative rate. So this is a negative quantity here, and this is indicating the loss of that reactant. So again, not an actual mathematical kind of thing. It's not a negative rate, because there just isn't such a thing from a physical standpoint. But by convention, we call any of these changes to be a negative for our particular quantities here. Now, if I was thinking about the rate compared to something like my NO2, now I have to factor this guy in. This happens twice as fast, or there's twice as many of these. So if I'm comparing that to the rate, then half of that amount, half of that rate is going to be my change in my nitrogen dioxide over my change in time. Okay, so my coefficient here becomes a fractional bit, right? So if this is 1 rate, this is happening twice as many, so it has to go twice as many, has to go in half the rate. And of course this would be negative. And then we are forming this product. So in forming this product, again, by convention, this positive is showing for products. Whoops. And it indicates gain. Then we have 1/2 of these guys too, because of this molar coefficient here, times the change of my NO2F over the change in time. There's my rate. Okay, so all of these are going to be equivalent to each other. So these are all equivalencies, and if I know the overall rate of the process, then I can find the relative rate for each of the different reactants and products. Okay, so kind of a wacky way to think about it, but ultimately what it's all about is that we can think about this as a change in the species over time. So the change in the reactants, we're getting smaller, right? Our concentration is going down as we react these things. So we can think about this as a negative quantity. That change is going to be based on the molar quantity in the balanced chemical equation. And all of these are going to be related in some way by their coefficients to the rate of the overall process. All right. Now there's kind of a lot of pieces to all of this, and we'll get into some more details here and do some practice with how this kind of plays out. So let's do this generalized example, because sometimes it's easier to just sort of take the chemistry out of it. Let's just call these reactants A and B, and my products C and D. So if I have an overall reaction rate of, and again, the overall reaction rate is always going to be positive, 0.500, and my units on this again are molarity per second, which is a change in concentration over a change in time. What are the relative reaction rates for each of the reactants and products? Okay, so if I'm setting this up then my relative rate for my A here, we just said that we have to base this on the coefficient. So we would say, well, negative 1/2 of the concentration of my A over the concentration in time has to equal my reaction rate, which is this, the 0.5 molarity per second. So the reaction rate has to equal 1/2 of this overall process. So if I kind of do some rearrangement, then that would be, you know, -2 times both sides. So that would give me a relative rate of negative 1.00 molarity per second. Now what you can see is if you're given a problem like this, then instead of thinking about it as a fractional thing, because sometimes that's kind of hard for students to translate because we're used to thinking about these coefficients as multipliers, then you could just think about it as a multiplier, right? What I essentially did is I said, well, it's a negative quantity because it's a reactant. -2 times this gives me the relative rate. So let's use that same kind of logic here for my B. My relative rate would be -1/3 of the change in the concentration of B over the change in time, and that has to be equal to my reaction rate, molarity per second. So the given, and so if I multiply both sides by my -3, then that gives me a -1.50 molarity per second. That's that rate of loss of my, or using up of my B in this chemical process. Okay, now let's go to C. C is a product, so we're forming it by convention. We talk about that as positive. So again, we're kind of thinking about this as a fraction of the change in C. Whoops, my brackets get a little bit loosey-goosey by the end of these lectures. Okay, and that equals my overall reaction rate, which again, if I multiply both sides by 4, then that will give me my positive 2.00 molarity per second. And then D, it's just a 1, right? So we can think about that as 1/1. It's going to be a positive amount. So that positive amount of 1/1 times my delta concentration of D over my delta T just gives me this same rate. Right? Again, if it's a 1-to-1 ratio, you can kind of think about this, well, this overall thing has this rate, and anything that has 1 in the overall reaction is going to have that rate as their relative rate. Okay, so kind of straightforward. You can kind of think about it in a couple different ways. You can kind of think about it as sort of solving the problem. How do I solve the problem and rearrange and solve for that rate? You know, I'd have to multiply both sides to get rid of the denominator, blah, 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 blah. Or you could say, well, I'm going to take, here's the reaction rate times the coefficient, right? 2 times this gives me this. I know that it's negative because it's a reactant. 3 times this gives me this. I know that it's negative because it's a reactant, etc. You can think about it both ways. That's why I'm kind of showing it to you interconnected, because I think it's easier to kind of think about in whatever way fits best with your understanding at the moment, because reaction rate stuff can be a little bit slippery sometimes. Okay, now just something to draw your attention to. If we look at the rates of the reactants, if we added these together, we'd get negative 2.50 molarity per second. And if we add these two together, we get positive 2.50 molarity per second. So net, then, I'm losing the same concentration of my reactants as I'm gaining of my products, which makes sense kind of from an intuitive standpoint. So it kind of jives in that way, internally consistent, which is kind of nice. All right, so let's think about some more implications of all of this. Let's look at another actual reaction. Now, the overall rate of the reaction is going to be limited by the slowest step in the process. So let's take the Haber-Bosch process here. This is the Haber-Bosch process, which is one of the most important reactions in the history of chemistry because of this formation of ammonia here. And ammonia is one of the reasons why we can feed the world's population, because that nitrogen is needed for plants in order to do their thing, photosynthesis-wise. And so the reason we can have the agriculture that we do to support the world's population is because of this reaction, because of these two scientists. All right, now if I'm thinking about this from a Lewis dot kind of standpoint, and then here's my ammonia. Now, in past videos, we talked about chemical reactions require to break bonds. So we have to put energy in to break bonds on the reactant side, and then we get energy out when we put them back together, right? Forming bonds is an energetically favorable thing. So it's lower energy. That's what energetically favorable means, right? We want to be the lowest energy possible. So this is a lower energy configuration than just having the pieces and parts all in the universe. So then there's going to be some energy that's released. So you have a certain amount of energy in, certain amount of energy out. That balance between the two tells us whether or not this is an endothermic or exothermic process. So we know that there's going to have to be some breaking of bonds, and then we have to form these guys. And each of these steps is going to have a rate that's associated with it, right? So I'm going to have 3 of these guys that I have to break, and it's going to take a certain amount of time to do that, time and energy. And then I have 1 of these guys I have to break, and that's going to take a certain amount of time and energy. And that's going to happen at a specific rate depending on things like temperature and pressure and catalysts and all sorts of other interesting things that go into changing the rate of a chemical process. And then these things will form at a specific rate, depending on the energetic conditions, depending on how quickly we rearrange things. These things have to collide together in such a way to where they bond together. So there's all sorts of interesting things going on. Collision theory says that the energy from this comes from these things physically bashing themselves together. So we bash these things together. If they do that in the right orientation with the right amount of energy, then we can end up with a product. And the speed at which that occurs is the overall rate of the reaction. So that's kind of what we're looking at here. And whichever step is the slowest, right? That's kind of like the weakest link, right? Whichever one is the slowest is going to be the one that limits the overall rate. So this overall rate is kind of calculated as a global average depending on the conditions. And then those relative rates are, if we look at the relative rates of each of the steps, then how quickly are we losing reactants and how quickly are we forming products. That change in concentration over the change in time. All right, more on this in future videos. If you have any questions on this relative rate stuff, don't hesitate to reach out. Otherwise, I'll talk to you again soon.